Welcome to the 23rd lecture of the course Turbulence. So, in the last lecture we talked about turbulent channel flow or wall bounded turbulent flow we started, and turbulent channel flow is one of such wall bounded turbulent flows. And for turbulent channel flow we consider a channel for which the height of the channel twice delta divided by length of the channel is much less than 1, and width of the channel divided by the length of the channel is much less than 1. Okay. So, for these particular channels we started finding out the the total shear stress tau Vt, which we found to be summation of Reynolds stress plus viscous stress, and viscous stress is dominated near the wall, Reynolds stress starts dominating as we go away from the wall. Okay. And as we said that as compared to the free shear flows, okay, or boundary free shear flows and the wall bounded shear flows, the main difference is the viscous stress. Okay. So, as you can remember, in the case of our free shear flows, while deriving the momentum equations using the order of magnitude analysis, we saw that our the viscous part of that equations can be neglected based on the order of magnitude analysis. But in the last class we have noticed for this particular case that from X momentum equation we found that one part of the viscous stress still remains in the equation, that is your the viscous stress. So, that viscous stress for this wall bounded case is important as compared to your free shear flows. Okay. This is one of the main difference that we have to keep it in mind. Okay. And central issues of this wall bounded turbulent flows, as I said, that basically the mean velocity profile and friction loss. Okay. So, this is what is our actually central issues for this kind of wall bounded flows. So, for these flows we got that the shear stress, total shear stress tau Vt, if you can remember, this is given by your tau W 1 minus y by delta. Okay. This is what we have got, where our tau Vt tau Vt equals to mu du dy minus rho u v, right. So, this part is the viscous shear stress and this part is Reynolds shear stress. Okay. So, tau Vt is summation of these two shear stresses. Okay. So, then while we drawn this particular profile with respect to our y by delta, we total shear stress varies like this. So, this is y by delta is equal to 1, and this particular tau Vt divided by tau W is equal to this axis. So, this maximum value is of course 1, as you can see at y by delta is equal to 0, the tau Vt divided by tau W is equal to 1. So, if you see the viscous stress, as you are slowly coming away from the wall, then its value starts decreasing, okay, and it's become almost 0 at the center line, whereas if you consider your Reynolds shear stress, as you are going away from the wall, that Reynolds shear stress starts dominating, and it increases its value as we go away from the wall. Okay. So, this is what is your y by delta is equal to 0. Now, this is in y by delta scaling. Now, if we plot this same thing with respect to our inner scaling, okay. Inner scaling means as we said in the last class, since that the near wall activities are dominated by viscous stresses. So, we found appropriate velocity and length scale near the wall, those are viscous scales. Okay. So, the velocity scale what we have got that u tau. Okay. So, u tau was our friction velocity. Okay. So, u tau is friction velocity which is defined by tau w by rho. Okay. Tau w is the wall shear stress, okay. And delta v is our viscous length scale near the wall, and that is nothing but a nu by u tau. Okay. So, these are the two scales, one is velocity, one is length, which are appropriate scale near the wall. Okay. That is what we have talked about in the last class. So, now if we plot in terms of this y plus, so y plus is nothing but y u tau by nu. Okay. This is what is your y plus, which is essentially y by delta v, because nu by u tau is nothing but your delta v, right. So, let us say if you plot this particular profile, let us say this is 20, this is 40 and this is 60, then you will see that your value, Reynolds stress value slowly increasing, at it's almost becoming constant near the as you increase the y plus value. Whereas, if you consider the viscous stress which reduces and approaches towards 0 as you increase the y plus. Okay. So, this is your actually this one is your minus rho u v divided by tau v t, and this one is your mu d u dy divided by tau v t. Okay. So, this is your the same thing tau v t. So, this is going to be then 1. So, tau v t divided by tau w. Okay. So, tau v t, so this is your 1. So, this value is going to be, so this value is going to be 1, because the tau v t is going to be totally mu into du dy at y is equal to 0. Okay. So, so anyway, this is what is the variation with respect to y plus, this is what is the variation with respect to y by delta. This plot was not plotted in the last class. So, anyway, after this profile, we talked about the velocity profile, right. So, the velocity is completely determined, or a channel flow can be completely determined by variable rho rho nu or rho mu, then your delta and u tau. Okay. So, these are the variable which will determine the velocity. So, if we go ahead with the dimensional analysis, then as we found that du dy is more important more important quantity as compared to your velocity. So, this is nothing but your y, this is your function of, we found y by delta v. Okay. So, this is what we found, that your dimensionally this is the velocity gradient can be written in this particular fashion, right. So, and then we come to that Prandtl postulation. Okay. What was that? That there is an inner layer very close to the wall. Okay. There is an inner layer very close to the wall. Within this layer, that the dynamics is governed by mainly the viscosity. Okay. So, that means this particular function, the limit of y by when y by delta tending to 0, this particular function y by delta v can be approximated as phi of 1 y by delta v only. Okay. So, this is within inner layer. Okay. So, within inner layer, so this is this approximation is valid. All right. So, if this is the case, then this particular equation we wrote as, this particular equation we can be written as then y plus 1 by y plus phi 1 of y plus, because y by delta v is nothing but your y plus, right. This is what we can write from this equation, right. Then what we got, that if we integrate, if we integrate, then this can be, so this implies after integration we can write this as f of w y plus, okay, where this f of w y plus is given as 0 to y plus 0 to y plus phi 1 dy, okay. This is what is your condition, and this particular equation, this particular equation is known as, okay, this particular equation is known as law of the wall, okay. So, this is important. Now, what we did next in the last class, what we did, we expanded this particular function near y plus is equal to 0, then what we can write, if we expand this function using Taylor series very close to the wall, then we can write this very close to the wall, this f w of 0 plus y plus f w prime of 0 plus the higher order terms, okay. So, at using the boundary condition or no slip condition at the wall, that f w, this particular quantity which is coming from this, so this particular quantity at y is equal to 0 is going to be, or at y plus is equal to 0 is going to be 0, right. So, that is what we have argued, because at y plus is equal to 0, that is f w of 0 is equal to u is equal to 0, right. So, that means this is equal to u 0 at y is equal to 0, and if we take the derivative of this function, then this derivative at y plus is equal to 0 becomes 1, that is also we have seen. So, that means very close to the wall, this particular equation can be written as y plus higher order terms, okay. Yeah. So, so that means very close to the wall, that u plus is a function of linear function of y plus, okay, and this whole goes for y plus less than 5, okay. So, for y plus less than 5, this particular relation is found to hold good, okay. So, that means if we plot this, if you plot this, then this is what is your let us say this is your y plus, this is your u plus. So, this is what is your u plus is equal to y plus, and actual data will deviate after, see, actual data will deviate after y plus is equal to 5, okay. So, this is what is your, this particular equation is nothing but u plus is equal to y plus, and this is what is your actual data, so which is found to deviate after y plus 5. That means, this particular approximation u plus is equal to y plus is well valid near the or very close to the wall, okay. So, this is what we talked about in the last class. So, today we are extend these discussions further, and let us see what we get. So, today we are going to talk about log law. Log law, okay. So, what is log law? That is what we will discuss, okay. So, what we found, our previous relation of dimensional analysis, that your so this is capital U, it should be, okay. So, u tau by y phi of y by delta v. What is the argument? Argument is that very close to the wall, this particular phi function becomes a function of y by delta v only. Okay. So, very close to the wall or in the inner layer, okay, as per Professor as per Prandel's postulation, that in the inner layer this particular function becomes function of phi 1 is a function of y by delta v, or that u tau y phi 1 is y plus, or you can write this particular equation du plus dy plus equals to 1 by y plus, just normalization, u velocity by u tau and y by y u tau by nu. Okay. So, then we get this particular relation, right. Now, if we consider the outer part of the inner layer, okay. So, inner layer is y by delta. So, inner layer extends. So, inner layer actually extends y by delta less than 0.1. Okay. Now, if we consider the outer part of the inner layer, that means if we consider the outer part of the inner layer, that means approximately 0.1, that is what we are talking about, then we can write this equation as y 0.1 delta, or we can write this as y u tau by nu. Okay. So, u tau by nu we are just multiplying in both these sides. Okay. So, u tau by delta nu, okay, or this quantity as we said y plus 0.1, and what is this? We defined Re tau. Okay. This is what we got. Okay. Now, let us say for Re tau very large, we are talking about y plus is much greater than 1. Okay. So, when we are far away from the wall, that means our y plus is much greater than 1. So, in that case this equals to 0.1 of Re tau, means Re tau is also large. So, Re tau is also large means we are essentially saying that Re tau is what? That your inertia force divided by viscous force. That means Re tau is large means in your inertia your viscous force is negligible, right. So, your viscous force is becoming negligible. If this is the case, then this particular function can be just a constant, or so based on this particular argument in the outer part of the inner layer, what we can write? This equation you can write as this equals to phi 1 y plus, it becomes a constant, okay, and this constant is essentially considered as kappa, okay, 1 by kappa. This is after von Karman, we will come to that, who did this analysis in 1930, okay, and this constant is after his name, von Karman constant. The value of that constant is 0.41. Okay. So, anyway, then it becomes constant if this is the case. So, what is the argument? At the outer part means when your y plus is much high, then your viscous force is going to be negligible. If your viscous force is not important, then this particular function becomes independent of y plus, means it becomes constant. So, that constant can be replaced with 1 by kappa, then this particular equation is equal to this, or from this equation what do we get? Du plus dy plus is equal to 1 by kappa y plus, right. So, if we now integrate this equation, let me do it here. So, integrating this equation, we get what? U plus equals to 1 by kappa ln y plus constant b. Okay. So, this is what we get. Okay. So, here and b are constant. Okay. So, who is vary 5% of the following numerical values, that is kappa is equal to 0.41 and beta is equal to 5.2. Okay. So, in the literature this variation of this kappa and beta constant can be 5% of these two values. Okay. But anyway, this particular law is after von Karman. Okay. So, this is after von Karman, okay, 1930. Okay. That therefore, this constant kappa is after his name. Okay. So, this is what is known as our log law. So, this is what is our this is what is known as log law. So, u plus equals to 1 by kappa ln y plus beta is the log law. Okay. Okay. And if we plot these in the inner variables, okay, or very often this particular log law is plotted in semi-log. Okay. Very often it is plotted in semi-log. Okay. So, let us say this is your 10, then 100, then 1000. Okay. So, essentially this is your let us say 1. So, this is in log scale. So, this log law varies, okay, and if you put your measurement data here, then it comes like that. Okay. Measurement data will come like this. Okay. So, this particular portion is essentially log law, okay, which is which holds good. Your 10 should be even closer. Okay. I am sorry, in this scale 10 should be somewhere here. Okay. So, this particular regime, okay, this particular value is about y plus is equal to 30. So, from 30 onward this particular law is seen to seen to be valid, okay, and this axis is y plus. Okay. So, this is what is the semilog. In this particular fashion, very often we plot this data, and your experimental data, which are this symbol, which are seen to be valid or will fall within this in this curve u plus is equal to y plus in this semilog plot till y plus is equal to 5. Okay. So, anyway, this is what is our log law. Now, if we see, we have already discussed some of the layers. So, basically a wall bounded turbulent flows, very close to the wall, we find various layers within which various laws or various velocity profiles are found. For example, this is what is your law of the wall, which is valid very close to the wall, and this particular function I may mention that it is a universal, it is a universal function. Okay. So, this is a universal function. Okay. For example, for pipe flow, for channel flow and for boundary layer flow, this holds good. Okay. And this u plus plus y plus less than 5, that also holds good for all these 3 flows. So, this is sort of universal function for all these flows. Okay. So, anyway, now if we find various layers, let me document this here. Okay. So, this is various layer, okay, and regions, and this is defining property. Okay. So, we know inner layer. Okay. Inner layer, okay, which inner layer holds good y by delta less than 0.1. Okay. That is what we call inner layer. So, what is the defining property of this inner layer? That mean velocity u, okay, mean velocity u is determined by u tau and it depends on y plus. Okay. It is independent of UC central line velocity and that channel half width delta. Okay. So, this is what is known as inner layer. Okay. Then another layer, viscous wall region. So, what is known? Viscous wall region. Okay. So, viscous wall region, okay, it is actually less than y plus 50. So, for y plus less than 50, the layer which exists is known as viscous wall region. What is the defining property of this? So, viscous wall region, so direct effect of viscosity direct effect of viscosity are significant. Okay. In this layer, direct effect of viscosity is significant. Okay. Next is viscous sublayer. Okay. Viscous sublayer. So, viscous sublayer, this is within this. Okay. I think let us write this is not region, location, and okay, that will be more appropriate, I believe. So, this is inner layer viscous sublayer and viscous sublayer. So, viscous sublayer, so that effects of Reynolds shear stress is negligible. Okay. So, that is what is viscous sublayer, which is within this. Okay. The next one is outer layer. Okay. So, outer layer which starts above y plus greater than 50. Okay. So, above y plus greater than 50 is known as this outer layer. So, velocity, mean velocity in outer layer is not affected by viscosity. Okay. So, the mean velocity is direct effect of viscosity on mean velocity profile is negligible, that is what also you can consider. Okay. So, that is what is our outer layer. Okay. So, further we have defining property, location, layers or regions. Okay. So, now after outer layer, the log layer or log law, okay, log layer. Okay. Location, log layer holds good y plus greater than 30 and y by delta less than 0.3. Okay. So, within this layer, that is log law hold good. So, what is the defining property? That log law holds good in this regime or in this layer. Okay. That is what is log layer. Okay. So, then after log layer we have something called buffer layer. Okay. So, buffer layer hold goods within this, okay. Within this region the buffer layer holds good. Okay. So, buffer layer exist between y plus 5 and 30. So, it is basically a layer within which the the region which is viscosity dominated region, or there is a transition from viscosity dominated region to Reynolds stress dominated region. So, this is the transition layer. Okay. The buffer layer can be considered as the transition layer from viscosity dominated region to Reynolds stress dominated region. So, that is what can be called as buffer layer. Okay. So, these are the kind of layer, and another one is there something called overlap layer. Okay. So, as you see your inner layer hold goods, or your inner layer extends till approximately y by delta 0.1, whereas your outer layer starts beyond y plus 50. So, between inner layer and outer layer there is a overlap layer. Okay. So, the last layer which is known as overlap layer, which is the layer in between. Okay. So, let me just draw this graphically here. So, the graphical the graphical presentation of this will be much better. So, let me do it here. This is your y plus 5, this one is your y plus 30, this is your y plus 50. Okay. So, and this one let us say y by delta. Okay. So, y by delta is 1 here, okay. Then 0.1 here, then somewhere here it will be 0.01, somewhere here it should be 0.001, and somewhere it should be 0.0001. Okay. So, that above scale is in terms of y by delta scale, okay. Lower scale in terms of y plus scale. Okay. Now, let us draw various layer one by one. Okay. Let us say use different color, okay, for better presentation. So, first our viscous sublayer, which is till y plus is equal to 5, viscous sublayer. So, this is this one is your let us say, let me write below, viscous sublayer. Okay. So, this is your viscous sublayer. Then your buffer layer. Buffer layer, let me use some other color. So, this is y plus 30, so y plus 5 to y plus 30. So, this is what is your buffer layer, right. Then viscous wall region. So, viscous wall region, it extends till y plus 50, this is what is your y plus 50. So, this is your viscous wall region. This is what is your viscous wall region, okay, till y plus 50. Okay. This is in log scale, okay, keep it in mind. So, next what we have viscous wall region, then we have inner layer. What is the inner layer? Inner layer, inner layer extends till this. Okay. So, this is what is your inner layer. Okay. And then you have outer layer. Outer layer y plus 50, y plus 50 is somewhere here, y plus 50 to, it starts from y plus 50 to this side. So, this is, sorry, I should have used some other color. Okay. Maybe I will use this color. Anyway. So, this is what is your y plus 50. So, outer layer. Okay. So, this is what is your outer layer. Okay. So, outer layer, then we have inner layer, then you have log layer. So, log layer holds good till y by delta. So, your log layer holds good till y by delta point 3. Okay. So, y by delta 0.3 is still that. So, that means your log law which validates from y plus 30 to this. So, this is your log layer. Okay. And we have you see we have a overlap, outer layer, inner layer. So, we have a overlap layer, outer layer, inner layer, we have a overlap layer. Let me use some other color. So, you see outer layer and inner layer, we have a overlap layer. So, this is what you see, this particular one. So, inner layer extends till this. So, this layer, then it is a sort of overlap between outer and inner. So, this is what can be called overlap layer. Okay. So, these are the various layers, okay, which is existing in a turbulent flow or in a turbulent channel flow, right. So, till this we could find two universal law, one is law of the wall, another is log law. Okay. So, these two laws actually are mainly determined by the viscous scales. Okay. Now, let us start talking about defect law. So, what is the defect law? Defect in the sense defect in velocity. So, it is defect in velocity means how much velocity is less compared to the center line velocity, that is what is your velocity defect. So, at a particular position whatever the mean velocity is there, so that mean velocity so center line velocity minus that mean velocity is the velocity defect. Okay. So, let us now talk about that particular velocity defect. Okay. So, we are going to talk about defect law. defect law. Okay. So, velocity defect is defined as, okay, velocity defect is defined as u c center line velocity minus the mean velocity at a particular location. So, this is what is your velocity defect. Anyway, if you remember that our dimensional arguments, that du dy can be written as u tau y phi of y by delta v, right. Now, here if you are far away from the wall, we can argue that the dependence on viscosity, this velocity dependence on viscosity is negligible. So, in that particular case, this particular function or relation can be written as phi 2 of y by delta, where this phi 2 so just 1 minute, where limit y by delta, for y by delta infinity, when this value is very large, then this particular function y by delta v, y by delta can be approximated as phi 2 y by delta. So, far away from the wall, the dependence on viscosity is negligible, okay, that we can forget. So, in that particular case, this functional dependence can be replaced with phi 2 function, which is just a function of y by delta. Okay. Now, if we integrate this particular equation, then you see we can write this as du u tau equals to 1 by delta phi 2 y by delta dy. Okay. Now, if we integrate, then we can write integrating, we get. So, if we integrate, we can write this as u c minus u divided by u tau equals to, we can write as integration y by delta to 1 by this phi 2 of delta d. Okay. So, we can integrate in this way, and this particular function we can call this as defect function f d y by delta. Okay. So, or we can write u c minus u tau. So, velocity defect can be written in this fashion as a function of y by delta. All right. Now, interesting point, this particular function or this particular law is for outer layer, mainly we are talking about. So, if you see one point, that in the outer layer or between the outer layer and inner layer, we do have a overlap layer. Okay. So, in the overlap layer, how this function is going to be. So, that is what we can argue in this particular case. So, in the overlap layer, we can write this velocity dependence, this particular equation. In the overlap layer, then you see in the overlap layer, this particular functional form, then can be written as how y by u tau du dy, okay. This can be written as phi 1 y by delta v, okay. Because in the inner layer we can write this equation in this fashion, in the outer layer this equation is going to be like that. So, which is coming from this phi 2 function. So, that means this is phi 2 which is y by delta, okay. So, this is what then we can write, right. Now, from this, okay. So, from this functional, now this particular function is equal to what? 1 by kappa, that is what we have found, right. So, that means from this what we can write for this overlap layer, y by u tau du dy is equal to 1 by kappa, and from here what we can write, you see, du let us say du u tau 1 by kappa y 1 by kappa y dy, right. This is the way we can write. Now, we can also integrate this equation to find this velocity defect, okay. So, integrating this particular equation, let me do it here, integrating what do we get? Integrating, we can write this as you see uc minus u divided by u tau equals to minus, okay. So, you can integrate this to 1 by kappa y dy, okay. This can be integrated to y by delta to 1, okay. So, if we do that integration, then u c minus u, because u c at the value when your y by delta is equal to 1, that mean velocity is u c, at any y by delta the mean velocity is u. So, this left hand side is this and right hand side, from this what you get, then you see you get ln y dash, which is ln y is equal to 0 minus ln y by delta will only remain plus some b 1, okay, plus some constant b 1 we can use here, right. So, you see here this particular functional form, okay. So, the in terms of velocity defect, okay, we have written this. So, 1 by kappa is missed here, okay, 1 by kappa is missed here. So, you see this u we can approximate at the center line using the log law. We can extend the log law till center line of the channel. Then this can be written as what? u c minus u c using log law divided by u tau. In that case, this value we are going to determine at the center line. So, that means log 1 which is 0, that means beta 1 or b 1, sorry. So, the b 1 is equal to this, okay. This is what you get b 1, and if you from experimental data as well as from numerical data, it is found that the value of b 1 is very small. For example, using DNS data, the b 1 value is found to be 0.2, whereas experimental data shows the B value is 0.7. Okay. Both these values are small, that is what it says. So, anyway, this is what is your this velocity defect in terms of log law, which can be written for the overlap layer. Okay. Now, one central issue which we have to address is the friction law. Friction law. Okay. So, before we proceed with friction law, let us find out the bulk velocity. So, bulk velocity from the previous law, what we can see, u c minus u b divided by u tau equals to 1 by delta 0 to delta your this u c minus u divided by u tau dy. Okay. As per your definition of bulk velocity, this is what we can write, and this particular function is going to be minus 1 by delta 0 to delta. We can replace the value of this, we can replace from this equation. From this equation we can replace the value of this quantity, of course considering V 1 is equal to 0, then what do we get here? We get what, that 1 by kappa ln y by delta dy. Okay. So, this value is approximately 1 by kappa, which is this is nothing but 1 by kappa, which is approximately 2.4. So, this value is also very close to the numerical value, which is found to be 2.6, and experimental data varies from 2 to 3. Okay. So, this is what is your bulk velocity which is related with friction velocity and central line velocity. Okay. So, it says that relation between the bulk velocity, central line velocity and friction velocity is given by this particular relation. Okay. U tau is equal to 2.4. Okay. Now, if this is the case, you see what we can do, we have got two equations. In the overlap layer our log law values. So, that means log law is what, u plus is equal to 1 by kappa ln y plus b. Okay. Or this can be written as u by u tau is equal to 1 by kappa ln, okay, this is y plus delta v, right, delta v plus b, that is what we can write. On the other hand, this equation is also valid, that is what we have argued. So, this equation is also valid in the overlap layer. If this is the case, you see, so this is one equation, let us say this is equation 1, and another equation is our u c minus capital U divided by u tau is equal to minus 1 by kappa ln y by delta plus b 1. Here the b 1 is a flow dependent constant which you need to add to that. Okay. It is a flow dependent constant, keep it in mind. I have forgotten to mention here, the b 1 here is needed because it is a flow dependent constant, and that value of that constant is found to be very small, which DNS calculation shows that it is 0.2, and experimental correlation or experimental data shows 0.7 based on various experimental data which has been used to figure out the value of B 1. Okay. So, let us say this is what is our equation 2. Okay. Now, if we add this, adding, okay, we get what? adding this equation we can say, see u by u tau will cancel. So, we will get u c by u tau, u c by u tau, and here if we see we are going to get so here we will get what 1 by kappa ln this minus delta v minus plus. So, delta by delta v it should be, okay, and it is becoming independent of y, that is the important point to note. Okay. So, plus what you get b plus b 1, okay, plus what you get b plus b 1. Okay. So, if we now do a little bit algebra, ln we can write this as this as let us say we will take one u tau, sorry, we will consider one u c delta by nu, and nu we have so u c delta by nu, or let us do another line. So, delta v is what nu y u tau. So, that means this is going to be u tau by nu, okay, plus b plus b 1. Okay. So, this can be rearranged. Let me do it here itself, we are almost done, or u c by u tau equals to what do we get 1 by kappa ln, this we can write as u c delta divided by nu, let me take, and u tau is there, u c is there. Okay. So, plus b plus b 1 or u c by u tau equals to, this equation can be written as u c, this is what REC, Reynolds number based on the half channel height and center line velocity, into this particular quantity can be written as u c minus u tau minus 1, okay, plus b plus b 1. Okay. You see, for a given Reynolds number, and these two values, what we can solve for? We can solve for u c by u tau from this equation. We can solve u c by u tau from this equation. Okay. So, u c by u tau, if we solve u c by u tau, then what we get? So, our CF, small cf, screen friction coefficient CF is defined as, this is by definition tau w by half rho u c square. If we consider, for this is for channel 4, if we consider the capital CF, by definition this is tau w by half rho u b square. Once we are normalizing by bulk velocity, this is what we call, this is what we call as capital CF, and if we normalize by half rho center line velocity, half rho u c square, then this is known as CF. Okay. So, if we consider this equation, you see how we can write twice tau w by rho u c square, right, which is nothing but, what is this, tau w by rho? Tau w by rho by definition u tau square. That means this expression is nothing but twice u tau by u c's whole square. Okay. So, this definition, this one is nothing but u tau by u c whole square, right. which is here, which is sitting here, you see, reciprocal of this is sitting here. So, that means CF, that means if we can solve this equation for UC by U tau, essentially we are solving CF. Okay. That means we are finding the screen friction coefficient for our channel flow. So, that is what one of the aim of this analysis, right, and that we can do it from this equation. Okay. Now, if we plot this, how does it look like? So, if we plot CF versus RE, RE means based on the bulk velocity. Okay. If we plot this, okay, CF versus this, for example, and let us say this is 0, this is 0.002, CF value is found to be very, very small, keep it in mind, 0.006, 0.008 and so on. For laminar flow, that friction law is something like that, okay, which is straightforward for us, and for turbulent flow it comes like this. For turbulent flow it is something like this. Okay. So, if you consider your experimental data, if you find the CF, your experimental data shows something like this. Okay. So, this is for laminar, this is for turbulent. Okay. And experimental data will come like that, and this is what is your transitional regime basically. Okay. So, this is, so that means this is going to be valid for more than Reynolds number RE for channel flow should be more than 2000, then only this particular regime is going to be valid. Okay. So, this particular that CF, how does CF should vary, is small CF here, that this axis, how CF should vary, this particular information can be found from this particular equation. Okay. So, this is what is the CF and the velocity profile. For velocity profile we got three, so CF is varying like that, and velocity very close to the wall is going to be u plus is equal to y plus, and then we found u plus for log layer u plus 1 by kappa ln y plus b. Okay. Then we found for defect law we found u tau which is minus 1 by kappa ln y by delta plus b 1. Okay. So, this is for overlap layer, but in general this can be written as a function of f d y by d. Okay. So, you see for channel flow our central issues were screen friction and velocity profile, and using the momentum equations and appropriate arguments, okay, we could arrive to these three velocity profile. So, velocity profile in a turbulent channel flow are sort of divided in some various layers. This is for law of the wall or viscous sublayer. This equation valids for y plus less than, so this equation is valid for y plus less than 5, okay, and this equation valids y plus greater than 30 and y by delta less than 0.3. Okay. And this is outer layer. So, this is valid for 50. Okay. So, that means velocity profile in a channel flow are divided by various profiles. 3 regime can be noticed in this particular case. Okay. So, this is what is our turbulent channel flow, and the central issues addressed through our momentum equations as well as proper arguments. Okay. We will stop here today. We will talk about the Reynolds stresses in the next class. Okay. Thank you.